This is Power Series Part 1. So this will be in 2 different videos. So basic definition of a power series is an infinite series that has the form where you have a constant times a power of x. That's why it's called a power series, and then you add them all up and it's infinite. And so we have been working with 2 different types of things that are similar called Taylor and Maclaurin polynomials, but this time we're infinite. So this one is going to infinity, but these will be very similar, and the first 2 types that we'll work with are going to be from doing a Taylor or Maclaurin process to get the power series, but there are other ways to do that. So the first one is a power series that's just centered at 0, and then the second one you can see is centered at C. And so that's important to know that, especially here in a little bit. So what's going to be important is that every single time you have a power series, basically this is a polynomial. Well, you can't always get a polynomial that equals exactly some function in every single part. For example, let's say that I have some graph that looks like this, and I've got this piece here, and then maybe down here, and then maybe this piece is up here. Well, let's just draw it down here and make it more obvious. Okay, so it's down here. So then if I were to find a power series and find a polynomial basically that matched this pretty good, I could probably get a polynomial that matches pretty good right here. So maybe it matches that function fantastically well right there, or matter of fact exactly right there, but the other places, the other parts that I drew, like over here, definitely don't match the rest of this function at all. So polynomials are of course continuous, so certainly if I'm trying to use a polynomial to emulate a non-continuous function, it can't work everywhere because there's going to be places that it doesn't work. So for example, on this one, maybe this is -3 to 3. So what we might say is we get an answer for this power series, but maybe the power series only converges on the interval -3 to 3. What that means is the power series only works for x values between -3 and 3. So anything in that range, you're going to get the same answer when you plug into the polynomial as you would if you plugged into the function. But it doesn't work anywhere else. And so that's what we mean by converges to. So that's when the answers will be the same. So as far as converging, here are the possibilities. The series could converge only at C. Now every power series converges at their center because that's how we generate basically the power series. If you'll remember the way we did that for the Taylor and Maclaurin, we made sure that the function, the first derivative, second derivative, third derivative, and so on all have the same values at C, whatever the center was. If it was Maclaurin, that was 0, or maybe it was around 1. So they have to have the same value at the center. But if you go away from the center, they may not converge at all. It may not be equal to the function at all. So number 1 says it's possible that it only converges at that one point, and that's it. Second option is the series converges everywhere for all x. So it's always the same, and we'll see some of those. And then the third case is that there's some place, some radius, capital R, that we're saying the series converges if we're within that distance of the center. So basically this inequality right here is the same thing as saying that x minus c is between -r and r. So we're saying that we have this ratio, or this radius, and this interval where the function is the same, like the one that I just drew. And then it's going to diverge everywhere else. Now the endpoints here, whether this is included or not included, is the thing that we'll have to test separately, and we'll look at that. And so we call the capital R, and it is capital. Remember, in math, we keep those things the same. So in, like, for geometric series, we use a little r, but here for radius of convergence, we use capital R. So if we're on number 1 right here, the series converges only at C, well, then the radius is going to be 0 because it only converges at one single point, so the interval has a radius of nothing, of 0. Second option is the series converges for all x. Well, then that means the radius then would be infinity because it would be true everywhere. And then if you had the third situation, which is what I drew right here, you're going to end up with some interval where you are the center minus r, the center plus r, and that's the interval of convergence. Now here, notice that you have a parenthesis and brackets, and that's because it could be true for one interval or the other, or it may not, or both of them could be included. So we have to test the endpoints. So this is important. We have an important note here. We have to determine if the endpoints, so we have to test them individually. And we usually use the ratio test to do these tests. And that's typically the first test we're going to go to, unless something's a p-series or a geometric series and it fits something else, obviously, then we can stick with that. But otherwise, a lot of times we just start with the ratio test, and then we'll just have to do something different if it comes out of 1. Okay, so let's look at example 1 here. So example 1 says find the nth term for the power series for e to the x, and then find the radius and interval of convergence. So the nth term means we also want to write this in the general form of it, so not just the Maclaurin series. Well, this is a series we already know, so we're not going to go through and generate this one because we've done this several times. This is one of those that you will need to memorize because you will use it quite often. So this is what the series looks like. So the nth term, we need to figure out the pattern. Well, the pattern's pretty easy to see, that you're raising x to the n, and then you have the same factorial. Because it's a series, it's dot, dot, dot. Now, technically, that xn, if I'm using n, then look carefully back here at the beginning and tell me what value of n am I starting with if I write x to the n over n factorial. So think about that very carefully. So if I were to write this out in series notation, I would have to use that starting point, which you should be able to tell is 0. So I have to start this at 0 in order to generate this series. Now, if I wanted to start at 1, I would just have to change that to x to the n minus 1 over n minus 1 factorial. So don't get too concerned about whether you're starting at 0 or you're starting at 1. Just represent the series in the way that's easiest to see. The pattern is what is important here. All right, so now what we're going to do is we're going to try to figure out where this converges. So we're going to use the ratio test. So we're going to find the limit as n goes to infinity of the absolute value of the n plus 1 term over the nth term. Well, here is my general term. So the n plus 1 term means simply put n plus 1 wherever you have n, and then divided by the nth term means times the reciprocal. So we do n factorial over x to the n. And then remember that ratio test is always absolute value, even though in this case it's not going to matter because we're going to get positive for the n parts. But the x could be any number here, so that's part of the reason we got to do absolute value, determine absolute convergence. Now we've simplified things like this quite a bit, so you should be able to figure out what we're getting here. So let's start with the x's. I have x to the n plus 1 over x to the n. Those are simply exponents, and we have the same base, so we just subtract. N plus 1 minus n leaves me just a single x. Then with the factorials, remember, n plus 1 factorial means n plus 1 times n minus 1, and so on. n factorial means n times n minus 1 and so on. So you're going to end up with just the n plus 1, because after you do n plus 1 times n minus 1, etc., this part right here is n factorial. So those will just go away and you'll end up with n plus 1. Now, here's the part that's a little different to remember. N is going to infinity. So when we're doing this limit, x here is actually a constant, because that's what we're trying to figure out. We're saying if you plugged in some number for x, so if I wanted you to do e to the third, that means x is 3. So x here is a constant. And when you're doing the limit, n is the thing that is varying, x is not. So we can actually take that absolute value of x and put it out in front of the limit, because it's just like pulling out a 2. You can just move it out in front because it's a constant. It is not changing. N is changing. X is some number. Now we can do this limit, so we'll still have our absolute value of x. We let n go to infinity. This is an easy limit we should be able to recognize quickly as 0. So my answer is 0 for the ratio test. Well, for the ratio test, we test to see how does that compare to 1. Well, this is less than 1. Well, if it's less than 1 for the ratio test, this tells me this converges. So this original x to the n over n factorial converges. Now I'm going to show you a shorthand for writing for all. That's a way to say for all x, a member of the real number. So that epsilon, this letter, Greek letter epsilon, just means an element of or a member of the real numbers. So this notation I will use quite a bit, because now we have to say when does it converge and that kind of thing. So here we want to specify this converges for all x, where x is a real number. So that's what that is saying. So this converges for all x. So if we wanted to write the interval of convergence, well, if it converges for all x, then the interval of convergence would be minus infinity to infinity. And then the radius of convergence would be infinity, because it's just infinite. It goes everywhere. So those are the types of things that you would be asked to answer. So there's an example of one that converges everywhere. All right, so let's go to the next one. So this one says find the radius and interval of convergence again. This time they've given you the nth term. So all I'm going to do is go ahead and do the ratio test. So I'm going to do absolute value of the n plus 1 term over the nth term. Now, I'm going to do absolute value, so I want you to think very carefully about this right here. What does that negative 1 to the n plus 1 actually do? Well, what it does is simply make something negative, then positive, then negative. It's an alternator. Well, if I'm taking the absolute value, then I'm just making everything positive. So it would be kind of pointless for me to write that. It's just going to cancel out with the other one, and it's going to just go away no matter what, because it's absolute value. So I don't deal with when you have a negative and it's just a multiplier like that, just you don't need it. So we just ignore that for this limit because I'm doing absolute value. So I want to do the n plus 1 term. So anywhere you see an n, you put n plus 1. So everywhere there's an n plus 1. So that's the n plus 1 term. Divided by the nth term, which means times the reciprocal. So flip over that nth term, and this is what we need to reduce so that we can take the limit. So let's work on that a little bit. So we have limit n goes to infinity, absolute value. All right, so let's start reducing. Well, we have again x minus 5 to the n plus 1 over x minus 5 to the n. So just like the last example, you have something that has the same base being raised to an exponent. So you simply subtract the exponents. That will leave me just an x minus 5 in the top. And I'm going to put in parentheses because there's some other stuff that's going to end up here in the top. Let's look at the n and the n plus 1. Well, there's no factorials here this time. It's simply an n and an n plus 1, and there's nothing I can do to reduce that. So those will just have to stay. And then let's look at the 2 to the n over 2 to the n plus 1. Well, again, all it is numbers that have the same base that are being raised to exponents. So you subtract and you'll end up with an extra 2 in the bottom. So you'll end up with a 2 in the bottom. All right, so again on this limit, I need to recognize that x minus 5 is actually a constant, and so is a 2. So we can take, and you will find it easier on these problems to go ahead and take out of the limit anything that is a constant that you can factor out. Now you can't just take out, like say on this n plus 1, you can't take a 1 out because that's adding. But we're multiplying by 2 and we're multiplying by x minus 5. So we can simply make the product of that go out in front. Just like if you had 7 times n over n plus 1, you could put the 7 in front. So you got to remember, x here is actually a constant. It's playing that role of a constant, and n is the thing that's changing. So now let's go through this limit. We have still our x minus 5 over 2 times, well, when we do the limit as n goes to infinity and we have n over n plus 1, you can either recognize that you get infinity over infinity and do L'Hopital's rule, and you'll get 1 over 1, which is 1. Or remember that we look at the powers there, and you have an n and an n, and so that will simplify to 1. So this is what we ended up with. So now we have to figure out, okay, so when does this converge? Well, again, we used the ratio test, so we know that it converges if we have absolute value of x minus 5 over 2 less than 1. That's when it will converge, because that's what the ratio test says. We have to be less than 1 for that ratio. So let's kind of solve this inequality. We're not going to do a whole lot here to solve it because we want to leave x minus 5. Because remember, if you go back up to this original problem, this one's different than the last one. This one is centered at 5. So we're trying to figure out how much do we go around 5 to get convergence, because we know it converges at 5 because all of them converge at their center. What we're interested in is where does it converge around 5. So we're going to actually leave the x minus 5, but I need to get rid of the 2. So I'm going to multiply both sides by 2, and I get this inequality. So when I look at this inequality, you need to remember back to your inequalities, this actually means that x minus 5 is somewhere between -2 and 2. That's one way to write it. And then all you have to do is add 5 and you'll get the interval here. So if I add 5 to all 3 parts here, so add 5, add 5, add 5, this means that we are between 3 and 7. Another way to realize what it's saying is just think about the words. This phrase right here is simply saying that you are 2 units away from 5 on either side. That's what that's saying. So 2 away from 5 means you're between 3 and 7. So right now we believe it's 3 to 7. We know at least it's that place. But the problem is we have to check the endpoints. So we need to go back up to this original function and we need to figure out what is happening. So we have to check the endpoints. So we found the big interval, the big part, but we got to figure out what's going on at those endpoints, and the endpoints were 3 and 5. So let's check x equals 3. So I'm going to go back to my original problem over here, and I'm going to plug in x equals 3. So I think that's all connected together. So I'm going back to this original right here, n equals 1 to infinity, -1 to the n plus 1, x minus 5 to the n over n times 2 to the n. And I'm plugging in 3. Okay, so I'm going to put 3 in. So if I plug in 3, That'll be negative 1 to the n plus 1 times 3 minus 5 to the n over n times 2 to the n. Remember, x is like a constant here. N is still going from 1 to infinity. So n still keeps changing from 1 to infinity. X is the thing I'm plugging in. So let's do some work to simplify this to see if it converges or not. So we're going to want to do a little rewriting. So we have negative 1 to the n plus 1, and this is actually negative 2 to the n over n times 2 to the n. Now, this right here, well, negative 2 to the n is the same thing as negative 1 to the n. So let me rewrite that. That's the same thing as negative 1 to the n times 2 to the n over n times 2 to the n. Because negative 2 means negative 1 times 2. So we have negative 1 to the n times 2 to the n. Notice that what that does is make that go away. And then you have negative 1 to the n times negative 1 to the n plus 1. So we got to figure out what's going to happen there. So when you're multiplying things that have the same base, you can add the exponents. So n plus 1 plus n would be 2n plus 1. Well, we did this not very long ago. We talked about what kind of number 2n plus 1 would be. 2n is always going to be even, so 2n plus 1 is always going to be odd. If you raise negative 1 to an odd power, you're always going to get negative 1. So that is going to end up simplifying to negative 1 over n, because ultimately this right here is just always going to be negative. And another way to look at it is negative 1 to the n plus 1 makes it negative every other term, and negative 1 to the n makes it negative on all the ones in between. Different every other terms. So you're going to get them all negative. So we've got negative 1 to the n that we're looking at. Well, if we think about this carefully, this is just the harmonic series, which diverges. That's the p series where p is 1, and it's called the harmonic series. And all we're doing is every number is negative. So it simply means it's the same numbers you would have for the harmonic series, only they're just underneath the x-axis instead of above. It is still going to diverge. So this diverges. So this is the divergent harmonic series. And then just write in parentheses maybe opposite. It's the opposite of it, but it's still going to be, it's still going to diverge because it's going to do the same thing. It's just going to do it underneath the x-axis instead of above, but it's still not going to come towards the x-axis fast enough. So that endpoint is not included. So far, we're looking at going from 3 to 7, and we just found out 3 does not work. So now let's try x equals 7. So we can go a little quicker here because it's the same thing, only you're going to do 7 minus 5, which is going to be 2 to the n, over n times 2 to the n. Well, 2 to the n, 2 to the n. So you're going to end up with an alternating series. And remember that alternating series is really easy to show convergence. You just show that 1 over n, with ignoring the negative, 1 over n goes to 0, which is true, and it's certainly decreasing, which is true. So this converges by alternating series tests. Now, when you are using these to prove the endpoints, you can cut a little bit out in what you say as long as you can justify it easily. Like the alternating series test is pretty easy to justify. The limit's 0 and it's decreasing. So as long as you can just say that and it's pretty obvious. Now if you started having a whole bunch of terms in there and it was not obvious it was decreasing, or it wasn't obvious about something else, the limit was 0, you can't really say that. But here this is one we've seen before and we know this converges. Okay, so what that gives me all together then is all of these things tell me that this series that I started with, x minus 5 to the n over n times 2 to the n. This series converges, or this, I'm sorry, don't want to just say converges, just say the interval of convergence So we say the interval of convergence is, now we said 3 did not work, 7 did work, so you'll have parenthesis on 3, bracket on 7, and then the radius of convergence is 2. Remember that inequality is going to be really easy to see. There's your radius right there. Okay, so your radius is 2 once you get the center isolated like that. Okay, so that one was a really long one. They won't all be that long. And I also went through it very slowly. Some of this stuff we've already done a few times, so you should be a little quicker at it. So let's do another one. So here we have x over 3 to the n. Now, for this one, we could do, certainly do the, we could certainly do the ratio test and all of that. But when we look at it, we should realize that this is actually a geometric series. And so to make life a little bit easier, let's just realize this is a geometric series. And the way you can notice that is you have a constant. This is a constant, a number raised to the n. So that's going to be geometric. Remember, x here is playing the role of a constant. It's just various things that can get plugged in, but it's a constant. So this is a geometric series. So it converges when the absolute value of r is less than 1. Well, the absolute value of r is the absolute value of x over 3. It will converge when that is less than 1. So multiply both sides by 3 here, and we get that it will converge when the absolute value of x is less than 3. So now all we have to do is check the endpoints. Well, the endpoints here will be a little bit easier to check because this is geometric. So to check the endpoints, so the endpoints of this interval are -3 and 3. So let's check x equals 3 first. So you'll have n equals 0 to infinity. If you plug in 3, you'll have 3 over 3, which is 1 to the n, which diverges. And that's easy to tell. Just do the nth term divergence test. And you can tell that very easily because the interval, or take the limit of 1 and you get 1, which is certainly not 0. If x equals -3, then you will end up with -1 to the n, because you'll have -3 over 3, which also diverges for the same reason. If you take the limit, you don't get 0. So we're going to get both of these endpoints diverging. So what that's going to mean is that all of that stuff together tells us that the interval of convergence is -3 to 3, because now we didn't get either endpoint to include, and the radius of convergence then is 3. That's the radius that we have there. So there's an example of one neither endpoint worked. All right, let's go ahead and do the next example. So again, here we're going to do the ratio test to try to figure out when this converges. So we're going to do the limit as n goes to infinity, and we're going to do the n plus 1 term over the nth term. Well, -1 to the n, again, ignore that because all the absolute value is going to do is get rid of those. And we need to do x to the n plus 1 needs to replace the n. So we have 2n plus 1. So we're going to replace the n with n plus 1. So that's 2n plus 2 plus 1, or 2n plus 3. Okay, so that's what's going to happen. So we're going to have x to the 2n plus 3. 2n plus 1 factorial, same thing will happen. That's 2n plus 3 factorial. Again, I don't need to consider that for the ratio test because of the absolute value. Okay, it's not gone, but I don't need to worry about it. So I have the n plus 1 term now. divided by the nth term or times its reciprocal. So just flip over what you have there. And again, just don't worry about the negative part. All right, so now we need to reduce this. So first we'll go with the exponents. So that's pretty simple. You've got x to the 2n plus 3 over x to the 2n plus 1. So that's going to be x to the 2n plus 3 minus parentheses 2n plus 1. We're going to subtract those endpoints. Well, 2n minus 2n is 0, and 3 minus 1 is 2. So we're left with x squared. Then we've got to figure out what are we going to do with our 2n plus 1 and 2n factorial and 2n plus 3 factorial. So again, think about what factorial means. 2n plus 3 factorial simply means 2n plus 3 times 2n plus 2 times 2n plus 1, and you would continue on like that, which is otherwise known as 2n plus 1 factorial. All you do on factorial is subtract 1. Okay, so I subtracted 1, I got 2, subtract 1, and then this is exactly the same as what the top is. So we're going to end up with just 2n plus 3 times 2n plus 2. The rest of that is all going to go away. Now remember, again, x squared is actually a constant, so we're going to pull it out in front, and then we're going to take the limit as n goes to infinity, 1 over 2n plus 3 times 2n plus 2. So as n goes to infinity, you're going to get 0 for that limit, so you're going to have x squared times 0, which is 0, which is less than 1 for all, which is what the upside down capital A means, x in the real numbers. So we say this converges absolutely for all x. Interval of convergence, if that's what you're asked for, is minus infinity to infinity. Radius of convergence is infinity. So sometimes we luck out. We don't have to test the endpoints because it worked for everything. All right, so we're going to do one more of these, and then we'll save the rest of this for the second part of the video. So here again, we have a limit that we need to take here doing the, we can do the ratio test. Or actually, right from the beginning, what do you notice? You have n factorial there. So let's say I wanted to do the nth term divergence test. I've got, or let's go ahead and do the, start writing the ratio test, but we'll see quickly what's going to happen. I'm going to put n plus 1n for each n, and then divide that by the term that I have itself. There's no fraction here, so it just becomes the n plus 1 term over the nth term. Well, this is going to divide out and just be an n plus 1. That's going to divide out and be an x minus 3, but all of that's a constant anyway. So what's going to happen as n goes to infinity? It's in the top, so you're going to get infinity. So this diverges. Okay, and we could have been able to tell that from the beginning from the nth term divergence test. There's no way plugging a number in for x was ever going to help that. It was going to diverge because of that n factorial. So this diverges absolutely. That just means in absolute value, which in this case didn't matter. It's not any, well, it could be negatives if x was negative. And so you're going to have the interval of convergence is going to be, well, none, because it doesn't converge anywhere. It converges only at x equals 3, and then the radius of convergence is 0. So there's no interval of convergence, so to speak. It's only going to converge at x equals 3. So we can even write that. Converges only at x equals 3. So this is only going to work if you're right at the center and nowhere else. So that's the end of part 1. And then, so just be looking for part 2 to finish your notes.